Hello and welcome to the Data Science Interview Prep podcast, where we discuss topics commonly asked about in data science interviews and give a high-level overview on those subjects. In today's episode, we'll talk about dimensionality reduction in machine learning, which is a concept that is important to understand as a data scientist or a machine learning engineer. We'll discuss first at a high level what dimensionality reduction is, and then we're going to deep dive a little into a specific reduction technique called the principal components analysis, or PCA. All right, so let's dive right in. So let's start with the basics and answer the question, what is dimensionality reduction? Well, dimensionality reduction is the process of reducing the number of variables in a data set by combining them into a smaller number of representative variables, and we can refer to this as the principal components. So to explain it in other words, let's make use of a simple analogy. I want you to imagine that you have a big box filled with a lot of different objects, and each object is like a feature or a variable in your dataset. To make it easier to understand and analyze the contents of the box, you might want to simplify the data by reducing the number of variables. So dimensionality reduction is like taking all the objects in the box and grouping them into a smaller number of categories. These representative categories are like the reduced dimensions or the principal components in your dataset. And now by doing this, you went from having a lot of separate objects into having a box with more grouped objects, and now you might be able to make more meaningful decisions since you can see things sort of at a more higher order level. So a second question you might be having is, why would we want to reduce the dimensions in our data set in the first place? Well, it might seem counterintuitive, but reducing your dimension space can actually be hugely beneficial in modeling. Dimensionality reduction is often used in data science because as the number of variables in a data set increases, the amount of data required to make meaningful predictions also increases. And also, as you might recall from a previous episode, having too many variables in a dataset can actually lead to overfitting, where a model becomes too complex and loses its ability to generalize on new data. To address these problems, we use dimensionality reduction techniques that decrease the number of variables in our dataset. So hopefully that all makes sense. Now let's think about when we would make use of this technique as a data scientist. So just imagine that you're working with very high dimensional data like images or text. It might be useful to reduce the dimensions in those situations. It's also very common to use in feature selection, where you need to choose the most important variables to include in your model. Another use case for dimensionality reduction is data visualization, where it can be used to reduce the number of variables in a data set to manage the number of dimensions. And once you do this reduction, you can easily visualize your results in a 2 or 3-dimensional plot. So now there are actually several techniques for dimensionality reduction, including principal component analysis, also known as PCA, linear discriminant analysis, or LDA, and T-distributed stochastic neighbor embedding, or TSNE. All of these dimension reduction techniques are used in machine learning to reduce the number of dimensions in a dataset. But do note that they differ in the way that they approach dimension reduction and the types of data sets that they are best suited for. So PCA is a linear technique that projects the data onto the directions with the highest variance. And PCA is best for datasets where the relationships between the features are linear and your goal is to preserve as much of the information as possible. And LDA is a bit different because it's actually a supervised technique that aims to project the data onto the directions that kind of maximize the separation between different classes. So this is a more suitable approach when you are working on a classification problem. And TSNE is once again a bit different because it is a non-linear technique that projects the data into a lower dimensional space. And it does this in a way that preserves the relationships between the data points. And as you might guess, TSNE is appropriate for datasets where the relationships are, of course, nonlinear, and your goal is maybe to create a visualization that helps to identify clusters. Okay, so if we summarize the key takeaways from these three reduction methods, we have learned that 1, PCA is a linear technique that finds the principal components of a data set, which are going to be linear combinations of the original variables that explain the maximum amount of variance in the data. LDA, by contrast, is a supervised technique that considers the class labels of the data. And TSNE is a non-linear technique that helps to reduce the number of dimensions. Now, as promised, we'll take a moment to deep dive into PCA, which is one of the reduction techniques that you're more likely to encounter in an interview setting. So again, recall that the PCA is a linear technique for dimensionality reduction. And how it works is it transforms the original variables in your dataset into a new set of variables that we call the principal components. And what these principal components do is that they explain the maximum amount of variance in the data. So we're going to do a simple kind of explanation walkthrough of the math behind PCA. And hopefully that'll help you get an intuition for what's happening under the hood with this process. So let's jump into the first step, which is standardization. In this stage, the original variables in your dataset are standardized to have a mean of 0 and standard deviation of 1. What this does is it helps to ensure that all of your variables are on a similar scale. And by the way, in case you are wondering, you can accomplish this using the standard scaler from sklearn. So after our data has been standardized, the next step in the process is to calculate what is known as the covariance matrix, which gives the pairwise relationships between all the variables in our standardized dataset. And if it's the first time you hear about this term, covariance is simply a measure of the strength and direction of the linear relationship between two variables. So now that we've successfully created our covariance matrix, we can go on to calculate the eigenvectors and the eigenvalues of that covariance matrix. And just for a brief explanation, the eigenvectors are the directions in the data that explain the most variance, and the eigenvalues are the magnitudes of the variances explained by each eigenvector. Now that is a bit of a mouthful, so if that sounds a little vague to you, let's try to understand these terms a bit more in detail. An eigenvector is going to be some non-zero vector in a linear transformation that, when the transformation is applied to it, it results in a scalar multiple of the original vector, okay? So an eigenvector results in a scalar multiple of the original vector. So in simple terms, an eigenvector is just a vector that when it's transformed, it only changes in magnitude and not its direction. An eigenvalue is a scalar that maps to each eigenvector, and the eigenvalue represents the magnitude of the transformation of our eigenvectors, okay? So basically, the eigenvalue gives us the factor by which we scaled our eigenvector. All right then, now that we have calculated our eigenvectors and values, we can move on to the second last step, which is the selection of the principal components. Here, basically, the eigenvectors with the largest eigenvalues are selected as the principal components. And these eigenvectors are used to define a new coordinate system that best captures the structure of the data. Now, finally, we can jump into the last step, which is the transformation step. Here, the data is transformed into the new coordinate system defined by the principal components. The result is a new set of variables that explains the maximum amount of variance in the data, which, as you might recall, is exactly what we're looking for. Now, these new variables are our final principal components, which can be used as inputs for a machine learning model. Okay, so I think that's enough for us to stop at today. There's been a lot of information in this episode, so feel free to go back and listen again if some parts were unclear to you. And that wraps it up for our discussion on dimensionality reduction and PCA. And as always, we wish you the best on your data science journey. So thanks for tuning in to today's episode of the Data Science Interview podcast. We hope you found this episode on dimensionality reduction helpful and informative. Be sure to join us next week where we'll discuss other interesting topics in the field of data science. Until then, happy modeling!